Hi, I'm Gilles Vismara, and together with Alessandro Verosimile, I will present a novel random forest accelerator for FPGAs. In the field of artificial intelligence of things, developers must respect hard constraints on latency, power usage, and accuracy. Random forests are a model that often helps fitting these three requirements by allowing both horizontal and vertical parallelization, and by relying on simple operations. For all these reasons, they are a perfect candidate to be accelerated with FPGAs on low-power embedded devices. State-of-the-art accelerators execute decision trees with a pipeline, where at each stage the required node is fetched from a memory element. Once a sample leaves the pipeline, it will have been labeled by a leaf node. As you may notice, this accelerator assumes that consecutive layers of a tree must be executed in series, but this isn't actually true. We could divide the tree into stumps, executing in parallel 3 nodes at a time. This way, we are essentially fusing together pairs of processing elements, resulting in a halving of the number of pipeline stages, which significantly reduces the memory needed for intermediate sample storage. This reduction of the hardware footprint allows us to fit more processing elements, which has the effect of doubling the average speed compared to the state-of-the-art running the same model, and enables the execution of forests with twice the number of trees. A configuration of our architecture can be synthesized by simply running this command with the appropriate arguments. Once finished, the generated bitstream can be found in this folder and is ready to be loaded with a random forest.
We tested random forest inference on the board on the seismic phase detection task, a real-world embedded application requiring stringent latency constraints. The input of the task is a 3-channel signal that needs to be classified among P waves, the first alert of a possible earthquake, S waves, the most destructive ones, an example of which is in the figure, and noise. Here you can see the definition of our accelerator with all the functions to load the samples in the buffer and to run the accelerator through ping. And then here we can see the code for the main execution. Lastly, here we import our bitstream and we can launch the inference. As you can see from the results that are going to appear, the inference is taking 0.68 microseconds and all the 3 samples have been classified with the correct class.